Hello, and welcome to today's lesson, Circles and Polygons, Unit 2. Okay, in Lesson 4, what we're looking at here is we're going to understand the properties of an inscribed angle, including when they intercept the same arc or same semicircle. We're going to understand the angle relationships in a cyclic quadrilateral, and then understand the relationship between two arcs that are intercepted by parallel lines. Now what we want to do is when we're looking at these situations, we want to make sure that we understand that there is some natural relationships that should make sense to us conceptually, and we want to apply those relationships to our process overall. Now, in one of our earlier lessons, we worked with central angles, and we know that the central angle and the arc that it creates are the same measure. Now what we have is we have what we call the inscribed angle. Okay, inscribed angle is using the same two endpoints as far as an arc goes, but the distance of the angle goes to the other side of the circle. Now we can tell visually that angle CAR is smaller than angle COR, and all we have to do is figure out, okay, it is smaller, what's the relationship between the two? So what I'm going to do is I'm going to draw a really quick angle, CAR, so we can take this and put it into the other angle. Okay, so as we're lining this piece up, okay, we can see that that's about half of it. And that's the true relationship between the two. Okay, if you're going twice the distance across the circle, your angle measure, your arc measure is going to get cut in half. So let's look at how that works exactly. Okay, if we're looking at it in an ideal situation, okay, we've got our central angle and our arc. We're looking at the triangles that we can create. And what we do is we create two isosceles triangles, and these angle measures are half of this angle measure here. Okay, so if we're looking at this situation, we know that the central angle is 105, we know that the arc is 105, and what you want to think about is as you're working your way across the circle, going back to this angle, you can see that that angle is getting smaller. So all we have to do to make that angle smaller is take that 105, divide it by 2, and we get 52.5 for our angle measure of x. So as you're going back to the angle from the arc, you cut it in half. As you're working from the angle out, you're going to double. Okay, so now, looking at this situation, we have to understand and look at some possible values that work from the inscribed angle. So now, we're working from the 30, we're working out. We can see that it's going to get bigger, especially compared to our central angle. So we're going to take that 30 and double it to get a 60. Okay, now, what we also have to understand is we have a diameter. So what do we know about diameters? Diameters create a 180 degree arc. So now we can solve for y. Y plus 60 equals 180, so y equals 120. Okay, now down below we have a very similar situation, but we're going to work this backwards. We know that the full arc is 180. We have 85 of it already to this point. So it means that the arc that we have left is 95. Okay, now if we want to find our angle x, you can see we're going into the small side of the inscribed angle. So when you're going from a large arc all the way across the circle, we have to remember that x is the arc length divided by 2. So we've got 95 divided by 2, or 47.5 is our degree measure for x. Okay, inscribed angles that intercept the same arc. So I have this angle here, angle APB, that intercepts this arc. Okay, and let's give this arc measure a distance. Let's call it an 80. Okay, and then we have a second inscribed angle, AQB, that's also intercepting the same arc. Okay, so they're both 80s. So if that happens, remember, we're working to the small side of the angle all the way across the circle. We're going twice the distance, so we have to take the 80 and cut it in half. So this angle is a 40, and since it shares the same arc, this angle is a 40. Okay, and that's our inscribed angles intercepting arcs conjecture. That's a mouthful right there. Inscribed angles intercepting arcs conjecture. Inscribed angles that intercept the same arcs are congruent, or have the same measure. Okay, now, if we have an inscribed angle inside a semicircle, okay, think about our rule. Okay, it's still an inscribed circle. The arc that it creates is a 180. So what's our rule as we work back across? We have to take that value and divide by 2, and it gives us a 90-degree angle. Okay, same thing down on the bottom. Okay, we've got our inscribed angle here, creates this arc on top, which is 180. When we work across to the small side of the angle, we have to understand that we're going to divide that 180 by 2, and that one is 90. Okay, so we can give you some questions based off of that. Okay, we know that our inscribed angle intercepts the diameter, so we now know that we have a perpendicular set of lines, 90-degree angle. We know that the arc on the outside is 180 degrees, or half of a circle. So now we can look at some of our other pieces. And remember, some of these diagrams are definitely not drawn to scale. Okay, we've got a 60-degree arc on the outside of this. Let's give it a name. We'll call it Y. So we have a 60-degree arc on the outside of an inscribed angle Y. We're going across past the center. So we know that Y has to be 60 divided by 2, or 30. And then we can use what we know about the triangle conjecture. The three angles of a triangle have to add up to 180. Okay, now we've got a quadrilateral inscribed inside of a circle. Okay, and what we will find out, okay, opposite angles of a cyclic quadrilateral are supplementary. Okay, or they add up to 180. Okay, now, why does that make sense? Okay, let's look at these opposite pieces. Okay, here's angle number 1. Here's the arc that it creates. Here's angle number 2. Here's the arc that it creates. Okay, those two arcs make up the entire circle. Okay, the entire circle is 360, but remember, we're working all the way across the circle. We're not working to our central point in the circle. So we know that angles X and Y, since they're inscribed angles and the arcs connected to them make up the entire circle, we know that X plus Y have to add up to 180, the entire circle divided by 2. Okay, so we can use that to solve problems, find missing pieces. Okay, if we have 95 here, we can find X. Okay, X is 180 minus 95, or 85. Okay, if this angle is 83, We know that the angle across from it in our inscribed quadrilateral is 97. Now, how can we find the measure of the arc y? We have to find something that connects to it. And always understand, if you're given information, there's usually a reason for it. So we want to look at our inscribed angle that includes the 100 plus y. So now we've got that arc on the outside of the circle, the 100 plus y arc. We know that that's across from the 97-degree angle. So as the 97-degree angle comes out, it has to be multiplied by 2. So then we get 100 plus y equals 194, and then we subtract 100 from each side to get y by itself. Let's just call it 94, right? Instead of 194. Okay, so we have to put together a lot of ideas, but the big thing that you want to do is make sure that whatever angle you're given, extend that so you can see the arc. Whatever arcs you're given, bring that back to an angle so you can make the connection between the angles and the arcs. Okay, we've got one last piece for today. We've got secant lines cutting through, and the secant lines are parallel. So remember what we know about parallel lines. We know that this distance and this distance are equal to each other. So if those distances are equal, it makes sense that this arc and this arc are equal to each other. So the x degrees here is x degrees here, and then that would also mean that this arc and this arc are equal to each other. And we could add up all the arcs to equal 360. Okay, so parallel lines intercept congruent arcs on a circle. So congruent is our main term we use to fill in the blank in that situation. Okay, that's our lesson for today. Good luck on the homework, and have a good day.